All right, we are starting off here with question one. We're doing a calculator problem. We're evaluating 9 factorial. So let's go to our calculator. The factorial is under probability. So we do math and then we go to probability. It's fourth option here. So you can just press 4, enter 362,880, which is choice C. And remember what 9 factorial is telling us? That's telling us the number of orderings of 9 objects. And remember that 9 factorial means 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Multiply all the way down to 1. Okay, next up we are evaluating permutations of 3 items from 12. So this is orderings of 3 from 12. Just remember, permutations take order into account, combinations do not. And if we go to the calculator here, that's again under math, and then probability, and then it's option number 2. And we want to put in the 12 first here. So 12, math, probability, option 2, and then a 3. So 12 NPR 3, 1320, which is choice D. And then remember that you can also get this from multiplication principles. You've got 3 objects out of 12 and you want to order those objects. So there's 12 choices for which one to pick first, 11 for which to pick second, and 10 for which to pick third. And 12 times 11 times 10 is 1320. Also, remember the formula for permutations. It's 12 factorial on top, and then 12 minus 3 is 9 factorial on the bottom. So this is 12 over 12 minus 3, 12 factorial over 12 minus 3 factorial, or 12 factorial over 9 factorial. And number 3, we're evaluating combinations of 8 from 15. So remember, this is selections. Order does not matter. Permutations, order matters. Combinations, order does not matter. So this is just selections of 8 from a total of 15. And the key presses here are going to be 15 NCR 8. If you use the formulas, then you'll have 15 factorial on the top, and then 8 factorial on the bottom, and then 15 minus 8 is 7, so 7 factorial. And we'll use the calculator to evaluate here. So 15. Again, math, probability, we are using NCR, which is option 3, and 8. 6435, which is choice A. Alright, so those were calculator problems. Now we're starting to apply our counting principles. So we've got a baseball team with 14 players. How many 9-player batting orders are possible? So orders here, so order does matter. So there's 2 ways to do this problem. You can either use the multiplication principle or you can use permutations. So if we use multiplication principle, then we've got 9 slots, 1 for each person in the batting order. And there are 14 players, so there's 14 choices for the first person in the batting order. And then they can't be used again, so there's 13 choices for who to pick second in the batting order. And then those 2 players can't be used again, not in this batting order. And so we get 2 less than 14, which is 12 choices left, and then 11, and so on, 10, 9, 8, 7, and 6. And then we multiply the choices at each step, and this is the 9th person in the batting order. And if you want to use permutations to do this, then this would be permutations or orderings of 9 from 14. So the total is 14, and we're ordering 9 out of the 14. So this again is going to be, the key punches would be 14, NPR, 9. And that'll give you the same answer as if you just multiply all these together. So let's key that in real quick. So we got 14, and then we're doing math, probability, NPR, 9, and we get quite a lot here. 726,485,760. So 726, 485, 760. Okay, order does matter. State uses license plates with 3 letters followed by 4 numbers. How many possible license plates are there? Repeats allowed. So order matters here again. So you always want to ask that question, does order matter? So order matters. I think the easiest way to do this one is with the multiplication principle. So let's first choose our letters. So we got 1, 2, 3 letters, and then we've got 1, 2, 3, 4 numbers. So these are our letters. And then these are our numbers or our digits. So we're allowing repeats. So for that first letter there are 26 choices. And then since we're allowing repeats, then we've still got 26 choices for the second letter and 26 for the third. And then for the numbers, this is actually digits. Digits are 0 to 9, so there's actually 10 digits we could use in that slot. We're allowing repeats, so all the rest of these are going to have 10 digits for both the first, second, third, and fourth number. And then we multiply the number of possibilities at each step of the process. So, and if we key this into the calculator, that's just 26 to the third power. Whoops. 26 to the third power times, oops, I want to arrow out of the exponent, and then times 10 to the fourth. So 17, well actually 175, 760. So 175, 760, 000. So 175,760,000. So lots of possibilities there. What if we do not allow repeats? Okay, then if we don't allow repeats, we have the same process with multiplication principle, same steps. Pick the first letter, second letter, third letter, first number, second number, third number, fourth number, just like we did before. But now picture the letters are in a hat. You've got 26 choices for that first letter, and then you take that out and set it aside. There's 25 choices left for the second. Take that out, set it aside. Now you've got 2 letters out, so 24 choices left for the third letter. And the same with the digits. So there's 10 choices for that first digit, but then you pull that out and set it aside. There's 9 left in the hat. Now you've got 2 out, so there's 8 left, and then 7 left. And then we multiply the choices for each step of the process. So this one, we just do the calculator work, just multiplying straight across. We will get 78,624,000. And you should double check my calculator work there. 78,624,000, 78 million. Still plenty of vehicle license plates here, even without repeats. But certainly not more than 175 million vehicles would be, for example, in the state of Illinois. Okay, number 6, we got a political science class, has 30 members, so that's our total. and we need to elect a 4-person committee for a class. How many ways can we do this? So we just want to select 4 people from 30. The order does not matter. So order doesn't matter. That's always the question you want to ask yourself. And so that tells us that this is selections or combinations, as opposed to orderings, which are permutations. So we've got 30 as our total, and we want to choose out 4. So 30 choose 4 is the number that we want there. And the key punches for that are 30 NCR 4. And let's go ahead and key that in. So 30, we're going to math, probability. NCR is option 3, and then 30 NCR 4 is 27405. Now also, if you did this from the formula, that's 30 factorial on top, and then 4 factorial on the bottom, and then 30 minus 4 is 26, 26 factorial. So that's how it would look like from the formula. So most of the time you won't need to use the formula. You can just compute with the calculator, but sometimes it's helpful. Sometimes you need to have that formula in general situations. Number 7, we're consisting the lottery. Usually with lotteries, order doesn't matter. And we are choosing 5 numbers, so that's selections, okay? So that's telling you order doesn't matter. And I actually made it clear here, order doesn't matter. 5 numbers from 1 through 48, so 48 is our total. How many possible ways to choose the 5 numbers? So 48 is our total, and we are going to choose out 5, so 48 choose 5. If we did this again from the formula, it's 48 factorial on top, and then on the bottom 5 factorial, and then 48 minus 5 is 43, so 43 factorial. If we're just keying into the calculator, this is going to be 48 NCR 5. Let's go ahead and key that in. So 48, math, probability, NCR is option 3, so 48 NCR 5. 1,712,304. Okay, so lots of possibilities there. And what is the probability of matching 4 of the 5 numbers? So this is asking now for a probability. So we're combining our counting principles with probability principles. So if we're going to match 4 out of the 5, here we're matching exactly 4 out of the 5. This doesn't say at least 4 out of 5. So we want to know what's the probability that we match 4 out of 5 of the 5 winners. And remember, the way that you want to think about this is you want to take your numbers and you want to divide them up into the winning numbers and the losing numbers. And probability is desired outcomes. So on the top here, we want to count the number of ways that we can pick 4 winners from 5 winners. So the number of ways to select, still order doesn't matter. 4 winning numbers, from 5. And then that from 5 winners. And then the other 1 number is going to come from the losing numbers. And then on the bottom is just the total number of ways to select 5 from our total of 48. No restrictions. So the bottom we've already done up above here. That's our 48 choose 5. So 48 choose 5 is the denominator. That's our total outcomes. And then desired outcomes, we would have 4 winning numbers and 1 losing number. So here we've got 5 numbers that are winners here. So we've got 5 winners, and then 48 minus 5 equals 43 numbers that are losing. So we're going to select 4 winning numbers from these 5. So there's 5 winning numbers, and we choose 4 of those winning numbers. And there are 43 losing numbers, and our other number to make up 5 numbers total, our one number that's left gets chosen from the losing numbers. So this is 4 winners and 1 loser. 4 winners from 5 winners, 1 loser from 43 losers. The AND is a multiplication, or means addition with probability. So the denominator we already have keyed in. That is our 1,712,304. We did that in part A. And then the numerator, 5 choose 4. That is actually 1. And 43 choose 1 is 43. So, no, I'm sorry, this is not 1. 5 actually. I'm sorry. There's 5 ways to choose 4 numbers from 5, because if you choose 4 winners, then there will be 1 loser. And there's 5 different numbers that could be losers, so that's this 5. And here, the number of ways to choose 1 from 43, well, you choose one of the 43 different choices. That's this 43. And then if you wanted to, you could write this as a decimal. So if you key that in, you get approximately 0.00013, which would be 0.013%. So quite a small probability. And then remember, if I would change this, so for example, just to kind of give you an idea here, if I said we're going to find the probability that we match at least 4 of 5, then that's going to be the probability that we match either 4 or 5 of 5. And the or is going to be an addition. So our denominator, so this is going to be or is addition, so this is probability that we would match 4 out of 5 plus the probability that we'd match 5 out of 5. Okay, well the first one we already did. The probability we match 4 is right here. So that's 4 winners from 5 winners and 1 loser from 43 losers out of our total of 5 selections from 48. And then the probability that you choose 5 of the winners would be you've got 5 winners here and you choose all 5 of those, and you've got 43 losers and you choose none of those. And then our total outcomes is the same, number of ways to select any 5 from 48. So notice the pattern here. 4 and 1 add up to 5, and 5 and 43 add up to 48. 5 and 0 add up to 5. So, and then I'll let you key this in for yourself. But this this addition comes from this or, and this multiplication here, and then also here, this is 4 winners and 1 loser, and 1 loser multiplication. 5 winners and 0 losing numbers. So that and is the multiplication. Okay, next up in number 8, we have a Bernoulli trial that's performed 20 times, where the probability of success is 0.4. What is the probability of, of 12 successes out of 20? So it's a Bernoulli trial. So a Bernoulli trial refers to binomial probabilities. So remember, that's where you have 2 outcomes. Probability of success is the same for all of your trials. The trials are independent, and then x equals the number of successes. That's our random variable. So the 20 here, that's going to be the number of trials, so n equals 20. Our probability of success is 0.4, so that's our p. P equals 0.4. And we want to know what's the probability of 12 successes out of 20. So that's telling us that our x, the number of successes we're interested in, is 12. So remember the binomial probability formula. Probability of x is equal to n choose x, and then your bases are p and 1 minus p. So the two bases of the exponentials add up to 1, and your exponents are x and n minus x. So these two exponents add up to the total number of trials. So what we need here is exactly the probability of 12 successes out of 20. So probability that x equals 12 is going to be, we've got 20, choose 12, so n is 20 and x is 12. And then our p is 0.4, so that means that our 1 minus p is going to be 1 minus 0.4, 0.6. So these two bases have to add up to 1. This power here matches the power on the p, which in our case is 0.4. And then these two powers have to add up to 20. So 12 plus 8 is 20. So 12 and 8 make our 20. And we'll go ahead and key that in. Let's see here. Looks like I need to refresh my calculator here. So let's see, we needed 20 and then NCR 12. So 125,970. So this number here is 125,970. And then we're going to multiply it by 0.4 to the 12. So times 0.4 to the 12th power. And then times 0.6 to the 8th power. 0.03549. So if we round that to 4 decimal places, 0.0355. Which would be 3.55%. And you can state your probabilities either as a decimal or a percent. Either way is okay with me. Now, this is a probability for just one value of the variable. I also want you to know how to find the probability for more than one value of the variable. So for example, I could ask here, what's the probability for this same problem? What is the probability of less than 3 successes? So that's saying the probability that x is less than 3. Well, there's 3 ways that you can be less than 3. If you're less than 3, you can be either 0 or 1 or 2. So this is going to be the probability that x is 0 plus the probability x is 1 plus the probability x is 2. So you add up the x values that satisfy this condition that you're looking for. So this is now going to be 3 copies of this formula. Okay, but they're all going to look similar. It's just that your value of x is going to change. So they're all going to start out with 20 choose, and then your x value is going to go down here. They're all going to look like 0.4 to a power and then 0.6 to a power. So all 3 pieces are going to look like that. So let me go and just make a copy of this. So we're going to have 3 copies of this formula. And then the first one is probability of 0. So a 0 goes down here. This exponent is 0. And then this is the number that adds to 20, which is going to be 20. 0 plus 20 is 20. Probability that x equals 1, so this will be a 1, 1 up here, and then these two exponents have to add to 20, so that's a 19. Probability that x equals 2, this will be a 2 down here. This is 2 exponent on p, and then these guys have to add to 20, so that'd be an 18th power. And then you would key all these in on the calculator. Okay, so that's how I could change things a little bit. And if I would have said less than equal 3, then you would add one more that you would have had to add on. Okay, next up we're doing some quality control. Lockheed Martin has determined that there is a 0.2%, notice that decimal point, 0.2% chance that the fuel system will fail on a particular model of the jet engine. 100 engines are sampled and tested. What's the probability that more than one fuel system is defective? So here again we're going to use our binomial probability formula. So let me copy that down. And we know that this is binomial probability because there's only two possible outcomes. They're either defective or not defective. It's a 2.2% chance that the fuel system will fail, so that's fuel system defective. So that chance is the same for any engine that you test. So the probability of a quote-unquote success, which means a defect or a failure in the system, is the same for all the trials. And these 100 engines, whether or not they fail, should be independent of each other. And then our x is going to be the number of defects or the number of system failures. So our n here we need, so n is going to be 100. That's our number of trials, which is the number of engines that we've sampled. And p is the probability of a success here, which is going to be 0.2%. So that's going to be 0.002. Remember, you always do p as a decimal. So that's 0.2%. Move it over 2 places. And then this is, again, the probability. This is the probability of a fuel system failure, which is what we're calling a success. So that equals a quote-unquote success. And then that gives us n, that gives us p, and then we need x. We want more than 1 is what we're looking at. Probability of more than 1 is defective. So what we want is we want the probability that the number of failures, x, is strictly greater than 1. Well, we tested 100 engines, so the number of ways you can be greater than 1, this would be saying the probability that x is equal to strictly greater than 1 would be 2 or 3 or 4, all the way on up to 100. And these are all joined up by ORs, so that's addition rule for probability, so we'd have to do this formula like, 97 times here, 98 times, and then add them all up. Well, we don't want to do that. That's just crazy. So we're going to do the opposite probability. So the complement here is going to be 1 minus probability of the complement event here, and the opposite of strictly greater than equal to 1 is less than or equal to 1. Okay, so the probability of an event is 1 minus the probability of the complement, and the complement is easier to count. So this is going to be 1 minus, and how do you get to be less than equal 1? Well, 0 or 1. There's only ways that x is less than equal 1. So we're going to subtract off the probability of 0, this is an OR, plus the probability of 1 defect. So we just have to compute these guys using the formula. So over here, let's do p of 0 equals, and then p of 1 equals. And then we'll plug those numbers in. So our n up here again is 100. For this first application of the formula, x is 0. Our p is 0.002. And then 1 minus p is what it takes to add up to 1. So 1 minus 0.002, which is 0.998. I need to refresh my calculator again. So 1 minus 0.002, 0.998. Okay, so that's this number here. And then the 0 exponent goes on p. And then this exponent has to add up to 100. So that's going to be 100 power. Okay, we'll key that in a second. And then for probability of 1, x is 1, so this will be 100, choose 1. P still stays the same, 0.002. And 1 minus p stays the same, 0.998. But now the value of x here is the exponent on p. And then these two have to add up to 100, so this has got to be 99 power. So now let's go ahead and key those guys in. So first 100, and math, probability, NCR 0 is 1. And we're going to multiply that by, well, anything to the 0 power is 1. So 0.002 to the 0 is 1. So we don't have to key that in. This is actually equal to 1. And so times 0.998 to the 100. So times 0.998. And then to the 100 power, 0.8186. Keep 4 decimals there. So 0.8186. So that's saying 81.86% chance that there's no defects. And then one defect here. So it's going to be 100, choose 1. So 100, math, probability, NCR1, which is 100. And then we're going to multiply that by, so it's going to be times 0.002. There's 0.002 to the first power and 0.998 to the 99. So times 0.998 and then to the 99 power. So 0.1640. And now we substitute these numbers in here. So this is going to be 1 minus 0.8186 plus 0.1640. Okay, so add those and then subtract from 1. And if you do the calculator work there, let's see what we get here. So 8186, so 0.8186 plus 0.1640 is 9826, and I'm going to do 1 minus 0.9826, so 0.0174. So which is a 1.74% chance. So just remember here that when you get a probability to evaluate and it involves lots of possibilities for the variable, you probably want to look at the complement. Alright, next up we are flipping a coin 4 times. That's going to be a binomial experiment. And we want to calculate the probability of getting 0, 1, 2, 3, or 4 heads. And then we want to draw the probability distribution where the random variable is the number of heads. Okay, so this is a binomial experiment. These are going to be Bernoulli trials. So we're going to use binomial probability formula. Because you've got 2 outcomes here, right? Heads or tails, and then we're interested in heads. So probability of heads is the same all the time. Probability of a success is going to be 0.5. And then our random variable x is going to be number of heads. So first, we want to calculate these probabilities. Well, let's go up and grab that probability formula here real quick. So this is our binomial probability formula. So we're just going to be using that guy for 0, 1, 2, 3, and 4. So probability of 0 heads. Well, we flip a coin 4 times here, so n is going to equal 4. Okay, so we've got this value n. We've already got our p. That's right here, 0.5. P equals 0.5. Probability of a success, which is heads. And then our x values are here, 0, 1, 2, 3, or 4. So probability of 0, we're going to have 4 trials total because we're flipping 4 coins. And then we're going to choose out, in this case it'll be 0. But let's go ahead and set up the general formula here. So this is going to be 4 choose x, and then our p is going to be 0.5. That's here. And then 1 minus p, 1 minus 0.5 is 0.5. So these guys add up to 1. And then your exponent here goes up here. Okay, so let's just make some copies of this. And then we'll fill in, because these all have the same form. So this will be for probability of 0. And this one will be probability of 1. And then probability of 2. Probability of 3. I need a little bit more room there. And probability of 4. So here we're doing probability of 0, so this will be 4 choose 0, and this exponent is 0, and this one has to add up to 4, so 0 and 4. Probability of 1 head, this would be 4 choose 1, first power here, and then cube here, because these guys have to add up to 4. 4 choose, probability of 2 is going to be 4 choose 2, this will be a 2, and then these guys have to add up to 4, so 2. So notice that these exponents on p are going up by 1, 0, 1, 2, and then this will be 3 and 4. And the exponents on 1 minus p are going down by 1, 4, 3, 2, 1, 0. And this is for probability of, I'm sorry, not 4, probability of 3, that's a 3. Probability of 4 heads, that's a 4. So notice that pattern. So it's just that same pattern over and over. So let's go ahead and compute these. We'll round to 2 decimal places. So first of all, 4 choose 0 for NCR 0 is actually 1. There's only one way to choose none from 4. 0.05 to the 0, that's equal to 1. So we really need to just do 0.5 to the 4th power. Okay, and looks like I need to refresh my calculator again. Okay, so 0.5 to the 4th power, 0.0625. So we'll just do 0.06. And then 4 choose 1, so it's going to be 4 NCR 1. And then we're multiplying by 0.5 and then times 0.5 cubed. So times 0.5 times 0.5 cubed. 0.25. And then 4 choose 2. So I do 4 NCR 2 times 0.5 squared times 0.5 squared. And that gives us 0.375. Since that's a terminating decimal, I'll go ahead and take it out, 375. Here, 4 choose 3. And then we're multiplying by 0.5 cubed times 0.5. Notice you can just multiply by 0.5 to the fourth power, 3 factors here and 1 more there. So times 0.5 to the fourth power, so 0.25. So this one's 0.25. And then 4 choose 4, that's going to be equal to 1. And then 0.5 to the 0 power is equal to 1. This is just 0.5 to the fourth again, which is what we got for a probability of 0. That's 0.06. And then if you add all these guys up, they should add up to approximately 1. So if we do 0.06 plus 0.25 plus 0.375 plus 0.25 plus 0.06 again, we get 0.995, pretty close to 100%. So that's a double check that you've done everything right. So these are the probabilities for all the values of this random variable, which is number of heads. Now we want to draw the probability distribution. So remember, this is just a bar graph where the height is the probability of the variable. So let's get our x and y axis going here. So your x-axis is going to be the probability, and then our y-axis here is going to be the value of x. So this is going to be p of x, probability of x, and then this is going to be x. And then we've got the values of x are going to be either 0, 1, 2, 3, or 4. And remember, we want our bars centered over those values. Now our highest probability goes up to 0.375. So why don't we go ahead and label this in tenths here. So 0.1, 0.2, 0.3, and 0.4. And now we just draw bars at the appropriate height. So probability of 0 was 0.06. So we do a bar of height 0.06. So that would be about right here, a little more than halfway to 1. And then probability of 1 right here is 0.25. So a bar centered on 1, it's going to go up to 0.25, about right there. And then probability of 2 is 0.375. So a bar centered on 2 goes up to 375. That's almost to 4, about right there. And then probability of 3 heads is 0.25. So a bar centered on 3, we're going up to height 0.25, which is going to agree with this guy over here. So like that. And then probability of 4 heads is 0.06. That's this height again. So a bar centered on 0.4 goes up to height 0.06. About right there. So there's our probability distribution, where x is the number of heads. So here this x is number of heads. And then these heights of the bars add up to 1. So the total heights of the bars add to 1. So just to check here, if you add all the p of x, then they add to 1. 1.00, approximately. So, and remember, this is a binomial probability distribution. That's one example of a binomial probability distribution. Then in number 11 here, we're finding the expected value for this given random variable. So we're given x and p of x, and remember that what we want to do here is we want to sum our expected value here, and we write that as e of x, that is the sum of x times p of x, sum of the value times the probability. So I think what I'll do here is I'll make a table, make a vertical table here, and we'll have 3 columns in there. So we'll have a column for x, a column for p of x, and then a column for x times p of x. And so our x values are 1, 3, 5, 7, and 9. And then our probability values 0.2, 0.5, 0.15, 0.1, and 0.05. And then down here on the bottom we've got a total row. Now these should add up to 1 exactly if it's a probability distribution. So 0.5 and 0.2 is 0.7, 0.05 and 0.15 is 0.2, so that makes 0.9, and then another 0.1. This is 1.00. And now the xp of x column, we just multiply straight across. So 1 times 0.2 is 0.2, 3 times 0.5 is 1.5, 5 times 0.15 is 0.75, 7 times 0.1 is 0.7, and then 9 times 0.05 is 0.45. And then if you add all of these up in the calculator, you get 3.6. Okay, and that total, that is the sum of the p of x column, value times probability, which is our expected value. Okay, so right here is our answer. So our expected value is 3.6. So whatever these values are, if they occur with these probabilities, we can expect that on average, the value of x is going to be 3.6. Now notice here, if we go back up to our coin experiment, this is a 50-50 split on each time you throw the coin, whether it's going to be heads or tails. So the expected number of heads that you would have if you toss the coin 4 times, you would think would be 2. And notice that 2, the expected value, is right in the middle of this distribution. Okay, so that's kind of a visual of expected value for that case. And that makes sense. You can see we've got half of the bars above, half of the bars below, and our expected value going right down the middle of that center bar. And then in the last question, we're analyzing a dice game here. You roll 1 die. If you roll a 6, you win $3. If you roll a 2 or a 4, you get $2, and otherwise you win nothing. Costs $1 to play. Will you win money or lose money in the long run? Show why in terms of concepts from the chapter. So this is just an expected value problem. What you want to do is you want to set up your table with x and probability of x, and then x times probability of x. And our x values here are going to be the amount that you would win, the different amounts that you could win, and that's going to depend on the outcome of the die. So let's put one more column on the front here for the outcome of the die. And so if you roll a 6, you win $3. So if your outcome is a 6, then you win $3, but it costs 1 to play. So your winnings there would actually be 3 minus 1, or 2. If you roll a 2 or a 4, you get $2. So if your outcome is a 2 or a 4, then you get $2, but it costs 1 to play. So 2 minus 1 would be 1. Your net winnings would be 1. So this x here is your net winnings. And then otherwise means the other 4 numbers. Okay, so that would be 1, 3, and 5. I'm sorry, other 3 numbers. 1, 3, and 5 is the otherwise. So if you get a 1, 3, 5, that's the other. Then you win nothing. So you win 0, it costs you $1 to play, so your net winnings are -1. You lose $1. And then let's compute the probabilities of these. So the probability that you roll a 6 would just be 1 chance out of 6. 2 or a 4, that's 2 chances out of 6, 2 numbers out of 6. And probability you'd roll a 1, 3, or 5 would be 3 chances out of 6. And now multiply straight across. So 2 times 1/6 is 2/6, because that's the x times p of x column, value times probability. 1 times 2/6, 2/6. And then -1 times 3/6 is going to be -3/6. And then we total those guys up. We don't need to total our x's here, but we total up our probabilities. 1/6 and 2/6 and 3/6 is 6/6, which equals 1. And that should always happen. That's a double check that you've done your probabilities correctly. And then if we total up the x times p of x, that's our expected value, our expected winnings. So our expected value of x, which is our net winnings, is the sum of the x p of x column. So we're using expected value to compute our expected winnings. So we add these guys up. 2/6 and 2/6 is 4/6, minus 3/6 leaves us 1/6. So 1/6 of $1, which is approximately 16 cents. And so our expected winnings here would be 0.16. So on average, you win 0.16, 16 cents, each time you play. So this would be a game that would be worthwhile continuing to play if you were the one that was playing the game. If you were the one that was offering the game to someone else, you're going to lose 16 cents approximately each time you play. So for us, we're asking, you going to win or lose money in the long run? We're going to win. And then why is because the expected value is the expected net winnings is positive. Okay, this is greater than 0, so it's expected win. If this was less than 0, then we would lose money on average each time we play.